We're very happy to have with us Imco Goudswaard, who is the sustainability lead at Endurans and has been in this field also for many, many years. So I'm very happy to have Imco with us talking about circular backsheets, protecting PV panels and the planet. Imco, the floor is yours.
Thank you for inviting me. And well, I'll give a presentation on circular backsheets. I'll try to catch up a bit of time. Oh, we can go to the next slide because I have no control over the slides probably. Yeah. Circular backsheets are important from a waste stream perspective. I think Jan was asking for a lot of waste, and for sure that's coming in our directions. Sorry. But perhaps before, no. Can you go one slide back? Before going into the circular backsheets, I can shortly introduce our company. I see the slides moving. Can you go back to the first slide? Yeah, this is okay. Yeah. So we were started in 2010, approximately 30 years ago, as DSM Advanced Solar. In 2021, we were acquired by American specialty film adhesive company called Wharton. And recently, we got a significant equity investment by Riverbend, which allow us to realize our growth ambitions. Amongst others, we will expand our capacity in the US. Next slide, please. Here in a nutshell, our company, I would say our key capabilities is in polymer science, in co-extrusion. We have two product lines at the moment, co-extruded backsheet for the regular front and back contact cells, and we have a conductor backsheet for back contacted cells. And we have production currently in Europe for conductor backsheet, in China and the US for the co-extruded backsheet. Okay, next. This presentation is about the co-extruded backsheet. It's a backsheet which, similar like the traditional backsheet, consists of three layers, two outer layers, so an inner and outer layer and a core layer. But it's a monomaterial-like product, so it's completely made out of polyolefins, polyethylene, polypropylene combinations. These polyolefins have intrinsic properties like electrical insulation, water barrier, hydrolytic stability, which secure the safe and reliable operation and lifetime of PV modules. I will talk about the sustainability aspects of this backsheet in detail. Of course, it's an affordable, price competitive product, which is mainly due to the use of these polyolefin materials, but also based on the single step production we have in manufacturing. Okay, next slide. So going to the circularity topic, for me this is one of the biggest issues we have. At this moment, there's hardly any waste because modules are there for 25 or 30 years in the field. And like it was already mentioned, probably the emerging waste stream will be visible starting from 2030. Can you go to the next slide? Cope with this waste stream, we need to change. If you just imagine how many modules will be there in 2050, if we want to reduce the global warming to 1.5 degrees C, there will be around 30 billion modules. So if you stack all these modules on top of each other, just to visualize how big it is, and then you can make a way to the moon and back again to Earth. So that enormous amount of modules and enormous amount of material which is stored there for 25, 30 years. For those who love the money. There's a lot of value in these materials which are stored in the modules on Earth. So we need to change, and we need to think about how we can turn this waste stream into value. Slide, please. A typical way to become circular is what also Jan presented. Is following the waste management ladder or waste management hierarchy, where you start to first of all reduce the amount of material you design in your product. Then you try to make the lifetime of your product as long as possible. Next step would be, and the priority is going down in this case. Then the next step would be to recycle all the components and materials at the end of life, or recover as much value from it, for instance, via waste to innovation. And if none of these work, then only landfilling is left. But then please make sure that you don't store or use any hazardous components, because that's highly risky, of course, if you landfill your product at the end of life. Now, if we translate this to the PV industry, next slide, please. And that's always helpful to have the butterfly model, which is often used in the circular economy, to show what's happening from the upper right, where you dig up the materials, and then to the left you produce your modules or your product, and then to the bottom right you dispose the materials. And in fact, we are not doing that bad as a PV industry. So, like I said, reduction of the amount of materials with the continuous increase of module efficiency or cell efficiency. We continuously also reduce the amount of material which is needed for 1 kilowatt hour or for a watt peak. So there we're doing fine. Also in extending, this is not an iPad which just has a lifetime or a battery lifetime of 5 years. It's there for 25 years, and we also have different ways to extend the lifetime, to reuse it or to repair some of the components. So also there we're doing well. But what we're not doing well still, that is closing the loop for materials or components. So most of the materials which we recover, for instance, in Europe under the DB directive, these are downcycled. So this is what we call an open loop cycling. So we don't extract the full value. We don't loop them back to our production anymore. So there we lose value. And we should do that, and we were continuously working on that. I saw the presentation from Imco to find new recycling technologies, which is very nice and very good, and an example of closing this loop to extract as much value as we can get from these PV modules, because we should not end up on the bottom right, where we either landfill or try to recover energy from plastics, for instance. Okay, next slide. From recycling perspective, what we do at this moment, also in Europe for the RE directive, is all focused on weight. And like Jan indicated, a PV module is almost nothing more than just a glass plate with some materials laminated to it. Most of the weight is glass. So if we set targets like 85% of weight recovery, that's quite easy, and especially if you don't add any targets to the quality of this glass. It's the glass at this moment coming out is not pure. You cannot use it again to make a PV cover glass. So we only extract something like 20% of the value in our current recycling processes, and we lose all the value from the silver, partly from the copper, and also from the silicon. So that needs to change. We need to shift also the RE directive from weight to value-based targets. Next slide. Yeah, if we now dive deeper into the backsheet situation. This is on the upper left, you see the traditional laminated backsheet with a PET core layer, often a fluoropolymer outer layer, or sometimes a coating, or it can also be highly stabilized PET film. And on the bottom, there's an inner layer, making sure it adheres to the encapsulant, which can be a fluoro, but also a non-fluoro based coating. In the production process, normally there's quite some waste produced. Last year that was around 15 kiloton, and that's from the edge trim. So these are the sides 2-3 centimeters at both sides, which are cut off because they don't fulfill the specs. And normally this is landfill in most of backsheet production is in China, and there this edge trim just simply ends up at the landfill. And of course, there are also options if we do that in Europe to send it to incineration plants. But then, for instance, if we use fluoropolymers, then we need to use special incineration plants which can withstand the corrosive gases of fluoro coming out, which really increases the cost of this incineration process. At the end of life, situation is not much better. It's difficult to get these backsheets off. Normally they go into the shredder, and then you need to separate the polymer and all the individual components. You can either landfill or incinerate it, and there are some good initiatives, since from Covema and DuPont Teijin, and perhaps also Cybrid. Sevencon will show something what they are doing, which focus much more on the recycling of the PET polymer. Problem with the traditional laminated backsheet is that it's a multi-material stack of film, and that makes it very inefficient to use a two-step process to get the maximum value out. Next slide, please. With the Endurans backsheet, it's the fully polyolefin backsheet. We can really close the circle. For instance, at first, that's at the production stage where you have the edge trim, because we use thermoplastic materials. We don't use any adhesives or coatings. We can just loop back our edge trim into our production line, by shredding and remelting the material. We can include this edge trim in our production process again. So there are zero waste. And at the end of life of a PV module, via a pyrolysis process, you can 90% back the polyolefin polymers to their monomers, and from these monomers you can make the polymers again. So that's almost a closed loop. There's something like a 10% char from the pyrolysis process, which is wasted. Slides. Here we have some numbers on the pyrolysis efficiency. Pyrolysis is an extremely efficient process for the polyolefin materials. You only have 8 to 10%, whether you have PE or PP of char, and all the rest of the weight is usable as a feedstock again to produce new polymers or other chemicals. And if you top to the fluoropolymer, the most used fluoropolymers in backsheets, there's a lot of char, 50%, and the same is for PET. And for PET, it's important to know that pyrolysis is probably not the most efficient process. There's a lot of research being done, and glycolysis processes, which is another way to chemically recycle PET, is more efficient. But then again, this is only for the PET film in the backsheet, and not for the coatings and the inner and the outer. Slide. Then to finish on circularity, of course, looping back the materials into the production chain is very important. but we should also consider the carbon emissions, because that's why we do this. We want to reduce the climate change. And there are quite some initiatives already, like eco design or the EP directive, which force the industry to lower its carbon emissions. Next slide. This is the last one. So this is showing the carbon emissions for backsheets, including production as well as the end of life situation, for two situations. On the left side, you have incineration. Then you see that there's already significant reduction in carbon emission for the polyolefin-based backsheets compared to fluoro-based backsheets. But if you would apply the pyrolysis process, then this reduction is, or this difference is much bigger, going to 90%. And with the polyolefin backsheet, you can almost reach near zero carbon emission. And that is a balance of the savings of carbon emission by reusing it as a feedstock again, and of course the emissions which come up from the pyrolysis process. That's it. Thank you very much.
Okay, Imco, very nice. I think very impressive. Let's maybe keep the questions for the panel in which you participate. I think we lost a few minutes.
Yeah, sorry about it.
No worries. But let's continue now so that we catch up in time. Thanks again. And we have now with us Stephen Gong,